That's a lot of that. That's fine. Like, okay. Make sure this works. Maybe. Not, we'll use the mouse. Anyway. Okay, sorry about the delay. Hello, I'm Nick Schragal. I'm a fourth year here. And I'm here to talk about near-infrared and also optical interferometry's role in reference star vetting for the Roman Space Telescope. So the Roman Space Telescope, specifically the Coronagraph Instrument, is designed to do exoplanet observations. And because this is an exoplanet talk, I must bring up the diagram. Hello, can you please switch? There we go. Okay. Yeah. Okay. So the diagram. This is, of course, this is the exoplanet. This is all the exoplanets that we know of that we have discovered, plotted with their mass on the y-axis and their orbital periods on the x-axis. Always have to start with this plot because it's important to get a context of what we're looking at. What part of this space are we looking in? And specifically with specifically with direct imaging, which the coronagraph on Roman is going to be doing, we look mostly at these planets. These are the planets that have been discovered by direct imaging. They all sit up here, but why? They are young planets, first of all, so they are incredibly bright. They are hot from their formation, and they are relatively easy to detect in the infrared. That's where most direct imaging campaigns happen. They happen somewhere in the infrared regime. And so we get all these young, hot, bright planets that are also far from their primary star, within the region where we can actually see them. If we want to go and search for planets that are like the planets of our solar system, for example, Jupiter, it is not young. It is really dim in comparison to those bright imaging planets. And if we want to look for something like Earth, it is none of those things. It is not young, it is not bright, it is not far from its primary star. So if most of our direct imaging campaigns happen in the infrared, in order to see these different planets, we have to go and look somewhere else. This is a collage of various different infrared images of directly imaged exoplanets. You can see that these are H-band and L-band images for 51 Eridani and Beta Pic. You can also see the scale. So we have the orbit of Neptune marked out in these two sub-images of this collage. So we're talking very bright, very far from their star, generally speaking. If we want to look for something like Earth, how do we look for this holy grail of exoplanet direct imaging? We have to turn to reflected light, of course, and that is what things like MAG-AOX have to shout out MAG-AOX because it's Arizona. That's what MAG-AOX is trying to do from the ground. Unfortunately, we are fundamentally limited with MAG-AOX because we're doing direct imaging from the ground. So you can see here on the right, there is a diagram of a dark hole that has been dug in simulations using IEFC on MAG-AOX. It can only achieve contrasts around 10 to the minus 7, a little bit deeper than 10 to the minus 7. And practically speaking, there is a limit to how far down in contrast you can go in ground-based imaging. So this is a plot of the flux ratio, the contrast, versus separation in arc seconds from the primary star. A couple of the solar system planets, Jupiter and Earth in particular, are plotted on this. And you can see the limits of various different missions, some space-based like HST, some like and JWST. There is VLTI gravity, the interferometer on the Very Large Telescope, and the general like ground-based limit of what we can do thus far. If we want to go and look for something like Jupiter, or especially if we want to look for something like Earth, we're going to need the Nancy Grace Roman Space Telescope. And specifically, its coronagraph instrument, because what the CGI is going to do, here's a nice picture of it on the bench, is it's going to take us from from the ground-based limit and the limits for our current space telescopes all the way down here to 10 to the minus 7 and lower. Specifically, these are the conservative estimates for 100 hours of imaging, 400 hours of spectroscopy, and 100 hours of a different of a longer wavelength imaging on Roman. It gets down to 10 to the minus 8, which is getting, these are the conservative estimates, gets really close to seeing Jupiter. If you take optimistic predictions for Roman, you can basically see Jupiter at 10 parsecs. So we're getting close. Earth is down there at 10 to the minus 10 contrast. So it's going to take more development. That's what habitable worlds is for. But the Roman coronagraph is the pathfinder for habitable worlds. So being able to see something like Jupiter not only allows us to see something like Jupiter, but allows us to see all of these different exoplanets that sit here below the ground-based detection limit. Where I'm at. Okay. So a quick briefer on the coronagraph on the Roman Space Telescope. This is the optical block diagram of the coronagraph. This isn't really a talk on coronography because I'm going to be talking about interferometry, but just we need some context as to what we're doing with the reference stars and what we need to do with interferometry therein. So with the coronagraph, there are two pieces that are very important. You have the low order wavefront sensing, which is basically an adaptive optics system. You go from the leftmost part of this figure to the second to right, just with a wavefront sensor and your typical, it's pretty much an AO system, just to gloss over many of the details. It's a normal adaptive optics system. If you want to do higher order wavefront sensing, which you need to go way, way down to 10 to the minus 8, you use the actual science camera on Roman to do this kind of wavefront sensing, where you are estimating the electric field at that camera based on observations of a reference star. So what you end up doing is you point your telescope at some star that you know doesn't have any companions, that you know doesn't have any dust or whatever around it, and you look at it with your coronagraph, and when you go to do your high order wavefront sensing, you iteratively change the actuators on your deformable mirrors that are doing your wavefront control. You iteratively adjust those to determine what your electric field is and to dig the control region around your star, so that you can see your planets and whatever other little bits and bobs you want to see around your star, right? To do this, you have to sense those tiny electric fields that are being introduced by stray light in that control region. And to do that effectively and efficiently, very important, you have to use a very bright star. And so this begins the quest for reference stars. What are the requirements that we need our reference stars to meet in order to be good reference stars to use to dig the dark holes, to be to construct point spread function models for Roman? First of all, they need to be bright, as I have mentioned. They need to have, the current limitation is they have to have a Vmag less than 3, visual magnitude less than 3, because higher order wavefront sensing time exponentially grows as V increases. So this iteration takes a long time. At V less than 3, it takes on the order of 10 hours. As you go down to V of 4, you start to get into days. If you go really, really dim, you might as well not even think about it. So V less than 3 is the current limit. You need your reference stars to be bright. You also need your stars to be low multiplicity. Ideally, they're all single stars. That would be perfect. They're all single stars. They don't have any companions. They have no planets around them, no disks. They're just a star. They're just a point source. We would like that, but acceptable is a wide separation multiple. So if you have a binary star that has a very large separation between its two components, that second component, we're talking on order of several arc seconds here. If your component is way out there, it's not going to pollute your control region. It's not going to pollute your dark hole. So you're good to go. as you can see here. So as you move a point source off of center at the focal plane mask on top and at the detector at the bottom, you can see its point spread function. It just comes through. And that's what it would look like if you, that's the contribution from a stray binary component. The problem with these two requirements is they put us in a very interesting regime of stellar multiplicities. For really, really bright stars, for our V less than 3 requirement, we're going to end up with A, B, and O stars, which on this plot of multiplicity fraction in blue and companion frequency in red, pretty much all of those stars are multiples. So we need to go and figure out which stars that are inevitably multiples are acceptable to use for Roman. The last thing is we need stellar size to be acceptable. We would like for our stars all to be less than 1 milliarc second in diameter. Acceptable, the current limit for what is a good reference star with Roman is about 2 milliarc seconds. And this is because if we introduce larger stars into the dark hole digging process, you introduce extra extra noise in the dark hole that resembles that of jitter. So what I have plotted here, taken from CHRIST 2023, there is jitter. This is specifically a plot of jitter's effect on the dark hole contrast, but there is a like similarity between stellar diameter and the kind of jitter it is related. The jitter that stellar diameter, the jitter-like noise that extra stellar diameter introduces into the dark hole. So if you have these simulations are done on a 1 milliarc second star with various amounts of jitter. If you have a 1 milliarc second star with 0 milliarc seconds of jitter, it looks like the left figure. If you have a 6-ish milliarc second star with 0 milliarc seconds of jitter, it looks like the right figure. So larger diameter, more jitter-like noise, you get less contrast. So we have a limit. We have our limitation there. So with all of that out of the way, let's look at what stars fall into these categories, because it's not many. First off, V less than 3, there are 183 of them. That's it. That is all of the stars in the sky with Vmag less than 3. 183. It's not a whole lot to start off on. The first refinement oh yes, couple notable things. Sirius is on here. It has a Vmag negative 1.46, and you can also see Orion on this plot. It's mirrored, but there's a bunch of pretty much all the like characteristic stars in Orion are visible on this plot. Anyway, going through the first refinement that the Roman's community participation program has done for the Coronagraph instrument. The first refinement of this list of all V less than 3 stars cut us down to 74 of them. You can still see Orion there, but it's getting sparse. And further refinement of this list, when we look at what are currently considered our good and our bad and our probably bad, but maybe not bad targets, we're down to 42 of them. So we're already, we're down to, I think this is like 20% of the original sample. And that still contains some questionable targets. If we just look at good stars, we're down to 24. And this is a problem because Roman has limits to where it can point between going from its reference star and your science target. So this is a different map. Justin made this. But this is plotted in ecliptic latitude and ecliptic longitude for a good reason. Roman is able to yaw in ecliptic longitude, but is not able to pitch in ecliptic latitude very far. It has a pitch limitation of only a couple of degrees. But it should theoretically be able to get a full swath in longitude based on a single star. So with all of the good question mark and bad question mark stars, the gaps in our coverage of the entire sky are shown in red. Those are regions where we just cannot see a science target. There is no reference star suitable for it. The optimistic case with the green and yellow stars, the good and good question mark stars, you see some more gaps forming. And if we only end up with the green good stars, most of the sky is gone. So you throw out a lot of science targets. If we just stuck to the very, very good stars that we're like pretty sure are good, they should work for Roman, this is what it would look like. So the real task ahead of us is how do we figure out if those good question mark and bad question mark stars are any good to use? And for that, we turn to interferometry. Now, this is going to be a real quick run through on interferometry because it's complicated. And for astronomers, it's more complicated because we don't get taught optics very well. So for the optics people in the room, sorry. This is going to be, I think you're going to probably know a lot of this.
That was. I have to go.
All right.
Did the jitter model include limb darkening?
No, I think it's a uniform disk.
But the limb darken diameters usually aren't that different from the diameters, at least for these.
Yeah. They're generally small. Okay, so interferometry. If you recall from basic physics, take a laser pointer, shoot it at a hole in a wall, you get your sync function out as your response from going through that slit. It's your simple Fourier transform. Your first null occurs at lambda over d, and this is equivalent to just having a telescope, right? Shine it through two slits, you end up with your double slit pattern. And this is the equivalent to having two different telescopes where you're feeding. So with this double slit, you have your lambda over d pattern, which gets you your first like major null. But with the baseline between those two slits, you end up with lambda over b being the spacing between the peaks of your fringes, right? So in essence, what you can do with two telescopes is feed them into these two parts of your double slit, and you end up with your double slit interference pattern, right? There is one problem here that you might be able to see. It is that the distance from that first telescope and the distance from that second telescope to these double slits don't match. So with a uniform wavefront coming into these telescopes, with these two different lengths of lines to your double slit, you won't end up with your interference pattern. You instead need to introduce delay. For radio interferometry, that's really easy comparatively because you just use an atomic clock. You can measure the electric field at any time basically and say, my atomic clock said it was this time when this wavefront passed. At this telescope, I needed to delay it by 50 microseconds. Bada bing, bada boom, slap it all into a computer, and you've got yourself an interference pattern. For optical interferometry and infrared interferometry, you can't measure the electric field at all times, so you have to do it on the fly. This is the CHARA beam combiner lab. And what you see as these like boxes in this image, those are the delay line carts. So those slide up and down on 40-meter long rails that essentially make all of the telescopes have the same distance from the target. That's what they're doing. You are artificially lowering your telescopes into the ground to line them all up and allow for interferometry to happen on the fly. And with interferometry, you end up with fringes. You don't end up with a picture, you end up with these fringes. East-west baseline, you get vertical fringes. North-south, you get horizontal fringes. And if you rotate your baseline any which way, you get your fringes in some direction or another. Of course, with a longer baseline, as you increase your baseline, you get fringes, you get tighter fringes. These are both from radio astronomy because they were the easiest to find. So you'll notice that it's a 5-kilometer baseline. We're not doing that with CHARA, but regardless, the other important thing is what is my coverage? if you think about the longest baseline in your array as the diameter of the telescope that you are synthesizing, the question then becomes, how much of this telescope am I actually, how much of the area of this telescope am I actually filling up? With 4 different telescopes, you end up with this arrangement of 4 telescopes, you're very sparsely sampled in the UV plane. Like your aperture is very sparsely sampled. And so you end up with this kind of, with the interference pattern shown at right. Increasing your number dramatically gives you a much better point spread function, gives you a much better interference pattern. And if you let the Earth rotate, you fill that out even more, right? So those are the tricks to interferometry. Let your double slit, use your telescopes in a double slit, let them interfere, record your fringes on the fly with optical, synthetically in radio, but specifically in optical. You are looking at those interference patterns. You are watching them as they change, and you are thus filling out your UV space. And so with optical interferometry, you have these kinds of baselines. CHARA is the one in blue. It is the observatory I was working on. I was taking observations on 2 weeks ago. It has a maximum baseline of 330 meters. VLTI, the Very Large Telescope Interferometer, is at the top. It's in red. There are a couple other examples. The Navy Precision Optical Interferometer is in green. That is over at Lowell. Keck interferometer is closed, unfortunately, but the Large Binocular Telescope Interferometer is still operational too. So we have a couple of choices of interferometer. Specifically, CHARA is the one that I was working at a couple of weeks ago. So this is what CHARA looks like. There are 6 unit telescopes, each one pointing at the star, unless it was last week where 2 of them were acting up. So throw 2 out, you've got 4 telescopes. And this is what the UV plane looks like for those 4 telescopes for one of our targets, Alpha Pegasus. You can see here, there are 6 baselines, so they all get traced out in the UV plane. You can also see the, you would normally expect for a monochromatic light, just that curve, but because because Merc and Mystic are spectrally dispersed, you get the vertical lines as well. The orthogonal lines. That's what that is representing. So you've got your big 330 meter telescope that you are synthesizing, and you are only sampling at those locations. You're only sampling the wavefront basically at the locations of those unit telescopes, producing your resulting fringes. So as I've been saying, we are measuring these fringes, specifically the intensity. So get rid of the bottom, flip it up to the top. And what we look for in interferometry is the visibility. It is the maximum fringe height minus the minimum fringe height divided by the maximum plus the minimum. You hope the minimum is 0. Because if the minimum is 0, you have a point source, your visibility is 1. If you have a resolved source, your visibility is less than 1. And you can see that in this kind of example. I've appropriated a binary star example to be a kind of pseudo-resolved source example, just by looking at 2 different points on a resolved source. You can see that the wavefront for component number 2 is slightly tilted with respect to that of component number 1. And that results in the fringes being offset. It also results in the combined fringe not bottoming out at 0. Hence, you're reducing your visibility. This visibility can be, if you plot your visibility based on baseline, you can determine the diameter of your star, which is one of the things that we want to look for Roman. So with a 1 milliarc second star, this is directly from CHARA. With a 1 milliarc second star, your visibility tails off until about 300. But you still have some visibility at 300 meter baseline. With a 3 milliarc second star, you're first bottoming out at 140 meters. So you can measure the diameter of your star. You can also measure limb darkening on your star. So if you have a limb darkened 3 milliarc second star, it looks like the blue graph, whereas a uniform disk looks like red. So it will change the positions of those nulls and change the shape of your visibility plot slightly. So stellar diameters is one thing that we can look for in CHARA, with interferometers in general. The other thing is binarity, multiplicity, more generally. So looking at that binary star sample, this very similar concept, just with 2 point sources, not an extended source that is actually raising your floor for your combined fringes. Instead, it's just 2 point sources, very simply creating that visibility loss. But what if you end up turning your binary star? So what happens if you take your primary, number one, and take your secondary and put it on top of it in this image? If you take the secondary and put it on top, you don't have a tilted wavefront anymore. They will kind of constructively interfere. You don't lose your visibility as much. And so as you rotate these stars through the sky, you will end up with a changing visibility as a result of them changing with respect to your baseline. So this is a plot from the, that got cut off. This is a plot from the Keck interferometer when it was still operating. This is a simulation of the visibility squared as a function of the hour angle of this a example binary pair with those two separations in milliarc seconds, x2 and y2. So you can see the visibility changing as a function of angle. The other thing you can do here is you can determine the binary flux ratio by where your visibility squared bottoms out. You can also determine your binary separation by looking at the separation of these peaks in your visibility squared. So those are two things that we really want to look for with the interferometers when looking at Roman's reference stars, is we want to look for the signatures of these binary stars. The last signature is that of closure phases. So you'll notice here that this interference peak has been displaced from the original center for the primary star. White is just a little bit to the right of pink. If we were to move the secondary over to the left, this interference fringe moves off to the right. This can happen because of atmospheric turbulence. If you have a slight displacement in your wavefront as it approaches one of your telescopes, you will end up with your fringes and your baselines moving over. And so to tackle that, you end up with closure phases. You end up looking at what are called closure phases. So starting with the first telescope on the right, you look at the change in phase of your fringes as you go to the second telescope on the upper left. You add the change in phase as you go to the bottom left, and you add your change in phase as you go back. That should sum to 0 if you have a point symmetric source. If you have an asymmetric source, it will not be 0. And binary stars are asymmetric. So with a binary star, you should have a non-zero closure phase. It could also be pi, but that's pretty much just how you end up summing these different phase shifts. But what this does is this allows you to eliminate the influence of the atmosphere on your interferometer. And in the case of binary stars, closure phases are a very good way of sensing, like, is this, questionable binary stars. It's a good way of sensing, of knowing for sure, is this actually a binary star, or is this or is this some sort of other asymmetric source? So that is interferometry in a nutshell. And we've gone through, like, why do we need to look for binary stars? So just to kind of summarize here and put things in context to sum it all up. So Roman's coronagraph is unlocking a new regime for very high contrast planets. The observations require astrophysically uninteresting stars. They need to not be binaries, they need to be bright, and they need to be non-multiples, small and bright, in order to dig CGI's dark hole and do it efficiently, do it quickly. The reference stars are generally very bright, but they're also very high multiplicity, and they also are on the larger end of main sequence stars if they're not giants, which are even larger. And so with interferometry, we are able to determine the multiplicity primarily of these stars, but also we are able to secondarily measure the size of these stars. You can measure size in other ways with, like, SED fitting, but that is why we are using interferometry. That is how we are using interferometry to look at the reference stars for Roman and determine, are they good enough for us to use come 2027. With that, I'll take questions. there are any.
I have a question. I guess it's as far as the targets that Roman will be able to look at, because it seems like extended sources are really a challenge for like digging a dark hole. Like the reference really needs to have a small angular size. So then the targets after digging the dark hole, are those also going to be small in angular size, or will there be some kind of more extended sources that Roman can look at?
Well, Roman will be able to look. The observing strategy with Roman is initially you go and look at your reference star, you dig your dark hole, and you say, okay, my dark hole, good enough. Let's go look at our source. Let's go look at our science target. And you leave all your stuff. You set your dark hole. You set all of your parameters for your deformable mirrors, and then you can go look at whatever source you really want to go look at. So you can observe disks, which are inherently an extended source. You can look for planets. I don't remember off the top of my head if there are limits for like how big the parent star has to be for Roman. I would imagine that with a larger parent star, you're going to have a similar issue. Wow, there's a lot of slides in here. You'll have a similar issue way back here. Yes. You'll end up with dark hole pollution from your star being larger. But you generally are digging your dark hole on big bright stars and going to smaller, dimmer stars that are your science targets. I guess unless it's like Epsilon Eridani, which is like 3.7, whatever. But generally, yeah, you can look for extended sources within the dark hole. It's since you're not doing active sensing as you're looking at your science target. You go to your reference star, look at your science target, go back to your reference star to touch it up, go back to your science target to go stare, and you do some touch-ups along the way. That's generally how you do observing, how you will do observing with Roman.
Yeah, so there's, so as Nick said, you're not actively doing any more iterations once you're on science. So you're kind of just thinking your DMs. In that sense, maybe you're still doing some actions, but probably not much.
Yeah.
And then most of the diameters of science targets that we look at, if they are main sequence stars, they are going to be smaller than 2 milliarc seconds most of the time. The exception is Alpha Cen. Alpha Cen is like 8 milliarc seconds because it is the closest star to us. So
does that fit in the dark hole? Like, I don't know exactly what size dark holes they're planning on digging. But...
It's I think currently it's like 3 to 9 Landover D.
Yeah, so the smallest inner working angle is like 110 milliarc seconds or so. So yeah, I mean it's not really going to be a problem for most targets unless you want to like look at Beetlejuice or something.
Okay.
Yeah.
But also, I mean, again, there's a difference between like what like residual speckle noise you might have in your dark hole as a result of like your science target having a big diameter versus your reference star has a big diameter, and that fundamentally limits how well you can actually do high order wavelengths.
Oh, okay.
So like once you've dug your dark hole, I mean,
You're good to go.
And like point at whatever you want.
Okay.
Yeah, big quotes.
But like
Within your pointing limits.
Yeah. So it's more critical for the actual higher order sensing digging.
Okay.
Yeah. Once it's dug, you're good to go.
So I guess one of the big things from the last run is that you weren't able to use all 6 telescopes.
Yes.
I mean, so the fact that you weren't able to use all 6 telescopes, do you think that's going to have a big impact on how good your data will be, or?
It's unfortunate because most of the targets, this is actually the worst case that we ended up with during the CHARA run. only 4-unit telescopes. Most of the time we were able to include, which one was it? We were able to include East 1, which is the bottom left telescope. As you get more and more telescopes into the interferometer, you end up with more options for closure phases to observe, right? So if you have more closure phase options, you are more sensitive to asymmetries. You also just have more baselines to work with in general, to look for visibility changes, to look for, because remember, all of this is orientation dependent. So with mostly 5-unit telescopes, the baseline does decrease significantly because we're no longer working with W2 way off to the right. When it comes to closure phases, there's still 5 choose 3, which is like 1, 2, 3. Like there's 4 or 5 closure phases to choose from with 5 telescopes. With 4 telescopes, you're really, really limited. And some of the closure phases are really tight. Like, for example, if you were to use this set of 3, so these 2 south telescopes and this east telescope, you have a very, very like tiny triangle. You're only sensitive to like that direction, basically. So with the degraded performance of CHARA during the run, it will hurt a little bit. With 5 telescopes, I think it'll mostly be okay. We'll have to wait and see once we actually reduce the data. But with 5 telescopes, it should be fine. 4 telescopes, it's iffy. The other question is though, the West 2 telescope was also just in a degraded performance state for most of those nights. So we'll see how the data from W2 looks as well. I'm hoping it's all right. Data reduction will tell all.
Okay, so when you're analyzing this data, you really are just looking at pairs, like you're mostly just looking at like baseline pairs one at a time, or like aside from like the closure phases where you
aside from closure phases, you look at your visibility. Your visibilities are visibilities of individual baselines, and so those have each baseline has its orientation in physical space, has its orientation in UV space, so it samples that direction in the like object space. So yeah, you mostly are looking at your individual baseline visibilities. You combine them together to get a more complete picture. But the visibilities come from individual baselines. And then when you go and do your closure phases, those are when you start doing circles, or triangles.
Okay, yeah. So then based off of like the coverage maps, then even with the sky rotating, there are definitely gaps in like the baseline coverage. So can you still recover information from those gaps like in the closure phases, or are you just blind to those gaps?
You are at least to some degree blind to those gaps. Yeah, you are at least some. I don't exactly know the answer to that question. I don't precisely know the answer to that question. New to interferometry, it's complicated. But yeah, I believe you're mostly blind. If you like if you have an asymmetry if you have an asymmetry in like the vertical direction, but you have a baseline. Yeah, if you have two points of light. It's this example. If you have like, if your secondary star ends up on top of your primary star here, that is not in the direction of your interferometer's fringes, you're not going to see any. You're not going to really see anything. Well, you'll see something slightly different, but it's lower signal to noise ratio at the very least. You won't get this like tilted wavefront and this phase shift that you would get by having it displaced in the direction of the baseline. You will, very conservative postulation here, you'll mostly be blind in those directions, if not completely. Yeah. Well, thank you.